Hey there, in this video we're going to continue our discussion of the derivative as a function, and we're going to talk about getting the graph of the derivative from the graph of the original function. So here we have this example. The graph of f of x is given, so this is our function f of x, and we don't know its formula, so we just have the graph. Use this graph to graph f prime of x. So we want to be able to, on this axis, graph the derivative. Now remember, f prime of x, what is f prime of x providing us with? It gives us the slope of the tangent line at any point. So we want to be paying attention to the slope. What we're graphing in this part is going to be the slope of the tangent lines. So one of the ways that I like to start off with is by finding where is the slope 0, right? Where do we have horizontal tangent lines? Because without any place to start on the derivative graph, I have nowhere to even begin. So I'm going to go to my graph of f of x and ask myself, well, where is the derivative 0? Meaning, where does the function have horizontal tangent lines? And it looks like we have two horizontal tangent lines, and that appears to be at -3 and at possibly 1. And so that gives me a place to start, because then I know, okay, when I'm graphing the derivative, the slope is 0, right? The derivative is giving us the slope. So the slope is 0 at -3, and it is also 0, we have a horizontal tangent line, at x equals 1. So I know that my derivative has to cross the x-axis there. This is where the derivative is 0. Slope of the tangent line is 0. So now I have intervals to look at. What about then from -infinity to -3? What's happening? Then from -3 to 1, what's happening? And then from 1 to infinity. So finding where the derivative is 0, where we have horizontal lines, helps me break up the interval, the real line. And now I can look at each individual interval. So from -infinity to -3, what are the slopes of the tangent lines doing? So if I was to draw myself tangent lines here, so imagine that they only touch at one point, right? So what are the slopes? I don't necessarily need the value themselves, but notice that in what direction is the line going? The lines are increasing, right? So then that means that the slopes are positive. So -3 to -infinity, the slopes of the tangent lines are positive. So -infinity to -3 here, my derivative is positive. So I know I have to be somewhere up here. So I know that it's positive. And then what happens between -3 and 1? What is the derivative? So if I draw tangent lines in this region, now my tangent lines have slopes that are negative, right? Less than 0. So in here, the slopes are negative. So I'm going to be down here somewhere because the slope is less than 0. So that means f prime of x is less than 0. So we're going to be underneath the axis. What about from 1 to infinity? From 1 to infinity, when you draw our tangent lines over here, we go back to the slopes being positive. And so the slope here is greater than 0, so f prime of x is positive. So that gives me an idea of what the graph is looking like. Right here, the slope is positive. Here, the slope is negative. So the derivative is positive, derivative is negative, derivative is positive. And so I can try to graph my derivative. So I know it's positive, but I have to cross 0, and then you go into negative. And at some point, you have to come back up to cross 0, and then you continue. And so this is my rough sketch of what the derivative function will look like based on this graph. Now, let me show you the graph together. So not too bad, right? Wasn't too far off from my rough sketch here. So there's our function in blue, and there's our derivative in red. So let me just recap. sort of what we had talked about. So notice that up here at this, the peaks and valleys is where the derivative is 0, right? You have horizontal tangent lines. So m is 0 here, meaning the derivative, the slope of the tangent line is 0. So it makes sense that there, the red one being the graph of the derivative, crosses 0. And then you have another horizontal tangent line here, right? The slope of the tangent line is 0, meaning the derivative is 0. So that makes sense that then our derivative function is crossing the x-axis, right? Because that's when the derivative is 0, the y value is 0. And then, as we discussed here, from -3 to -infinity, or -infinity to -3, our slopes of the tangent lines here are positive, so it makes sense that the derivative there is positive. And then here, the slopes of the tangent lines are negative, and so we have our slopes are underneath the axes because they're negative. And then from 1 to infinity, our slopes become positive again. So you cross 0 and then you go on the positive side again. So that's how we can get the derivative from the graph. So a good exercise would be take your, something we know fairly well. So take your y equals x squared, right? This is a parabola. Can you graph the derivative from here without finding the derivative, so the derivative function? So just from the graph of y equals x squared, just from the parabola here, can you graph the derivative? And I think that you'll find that it's not too bad to do it. And then move to what about y equals x cubed? This is another one that we hopefully know what the graph of this looks like. This is what I call the John Travolta function, right? So we go, that's what it looks like. Can you graph its derivative from the graph of the original function? So these are good exercises to try. So how can you go from the graph of the original function to the derivative without knowing, like if you didn't have the formula? And the last thing I wanted to talk about is notation for derivative. So I know we have talked about the derivative is denoted f prime of x, but there are other notations that you'll see. So other notations include dy dx. So this means the derivative of y with respect to the variable x. So, because remember, y, f is a fancy name for y, right? So when you have d dx of f, right? So this is df dx, so the derivative of the function with respect to x. But when f of x is just a fancy name for y, so then you can call it then dy dx. You may also see things like the capital D and little x, f. So that means the derivative of f with respect to the variable x. And other notation you might see is f of x, and then the brackets or parentheses, and then the prime is on the outside. So that still means f prime of x. This is used when we have multiple functions, like if I had f of x times g of x and I want to find the derivative of that. So you'll see this when the function inside is more than just one thing. So these are different notations, they mean the same thing. So the standard one is f prime of x, but you will see dy dx quite a bit and df dx as well. Okay? Contact me if you have any questions.